Good morning, Year 10. This is Ms. Teresa. Today we are going to talk about thin converging lens. Our lesson objective for today is to describe the action of a thin converging lens on a beam of light and success criteria. I can define the basic terms related to a thin converging lens and explain the rules of drawing ray diagrams. So, first we are going to define convex lens. What is a convex lens? A convex lens is also called converging lens. It is a lens that converges rays of light towards a single point on its principal axis. It is bulged outwards with relatively thick middle and thin upper and lower edges. So as you can see in our diagram over here, this is a rough representation of a convex lens. It has thin upper and lower edges. It is bulged outwards and it is called converging lens. But why is it called converging lens? Rather, why and how does it converge light rays? So to understand, we will first have a recap about prism. This is a prism. Okay, a prism has three non-parallel interfaces. I'm going to show you that. So these are the three non-parallel interfaces. Okay, so when a beam of light, let's clear that up. When a beam of light is directed over here from this interface, this is the incident ray. So our normal will be drawn this way, perpendicular to the first interface. This is your incident ray. Now the tendency of a light will be, this is your angle of incidence. Okay, it will bend towards the normal. So how do you know it has bent towards the normal? It is this angle. The refracted ray is less than the incident ray in here. So this is your refracted ray. Okay. Now as it reaches the next interface, there's another normal. We can draw another normal here. Now this is from a dense medium, dense, to a less dense medium or rarer medium, less dense. So it will bend away from the normal. Okay, here. So this is your angle over here. This is your angle after it has emerged from the next interface. So this is quite larger than the angle here. So it will bend away from the normal. That's the normal behavior of light as it goes from less dense to denser, and then denser to less dense. Now in all prisms will have a light ray behaving this way. Okay, it always bends towards the wider end of the prism, always towards the wider end. Now how is this relevant to a thin converging lens? You say the shape of a prism is quite different from a lens. So let's go to our next slide for that. Okay, let's look at the shape of a lens closely. Here it is. This is a prism. This is another prism, although incomplete. The tapered end is not there. This is a kind of prism also, although tapered ends are not present. And then it will stack against this also, and finally this. So as you can see, if we can cut a lens into smaller parts, then it will look like this. Okay, it would look like a stack of one prism on top of each other. The shapes are not the same, but they are still prisms. Now let's look at how light rays, monochromatic light rays, will behave as they go through these series of prisms that make up a lens apparently. So first we are going to look at the middle one. This one is the easiest. Why? Because if we have a light ray from here, you know that this is perpendicular to this interface and it has parallel interfaces, therefore it's easy. It will just go through like this. Okay, unbent. Okay. And how about at the upper, this one, this prism number 1. I told you earlier in the previous slide that if a ray of light is originating from here, it will bend slightly inside the prism, and then it will bend, the emergent ray will bend towards the wider end, so it will look like this. Okay, and how about the lower one, the lower complete prism that we have? If a ray of light is incident from here, okay, it will just do the opposite thing that the other prism on top has done. So the light ray will bend towards the over here, and then it will bend away towards the wider end of the what's this prism, and then it will continue doing it like this. Now, as you can see, it has converged. This light rays converged at one point. Okay, and if we are going to continue for the other two prisms which are incomplete without the tapered end, it will also, the light ray will also behave this way and bend towards that, as well as this one, and it will bend towards that. That's why this is called a converging lens, because all the light rays which will pass through the lens, if this is a complete lens, okay, it will bend towards a single point on the principal axis. I mentioned principal axis twice already. It is one of the terms related to lenses, so let's define those words for us to understand better. First, we have optical center. Let me just draw something. So this is the optical center of a thin converging lens. It is denoted by big letter O. The central point of a lens is called the optical center. We can draw an imaginary line through it like this in broken lines. Okay, through this line, all the light rays will pass through and deviate or bend from it. So example, we have this one, incident ray, and then it will touch the line going through the optical center. Here it will bend from there this way. So that's the optical center. Next is the focus. The focus is a point at which all the rays of light converge, as we have seen earlier. If I'm going to draw a line over here, okay, so this is the optical center. We have 2 points, foci actually, F1 and F2. These are the foci of the optical lens. Okay, so they are equidistant. Both of them are equidistant from the optical center. One will be the principal focus only. So how do we know which one is the principal focus? It depends upon where your object is. So example, if example, this is F1 and F2. If example, our object is here and our light source of course will be here, the light rays will be emanating from this point. So we have a line drawn over here, then this will converge at one point. So let's make our object bigger. So all of the light rays coming from the object will be bent through the lens and like this. So we have one point at which they will all meet together. So this is the principal focus in this case. This is your principal focus. Okay, so in this case, this is our principal focus. But if example, we have here F1 and F2, or vice versa, it doesn't matter which one is F1 and F2 as long as they are equidistant from the optical center. If our object is over here, light source will be over here. So all the light rays will be coming from this side, and then they will converge at the other focus on the other side. So this will become your principal focus in here. So it depends where your object is. Okay, your principal focus will be dependent on where your object is. Next is our focal length. So as I have mentioned earlier, we have an optical center here, and the first focus is over here, and this is the second focus. The focal length is the distance between the optical center and the focus, any of the foci actually. So here are your focal lengths. This is focal length, okay, and this is also a focal length, this one. So they are equidistant from the optical center, both of them. Next is the center of curvature. What is the center of curvature? It's the center of the spheres where the convex lens is a part of. If that is too technical for you, then here is a diagram. So there are two spheres, as you can see here. Now they meet at this point. Now this point, this space actually is your lens, your thin converging lens. So these two spheres, they have centers here and here. Now these are called your centers of curvature, C1 and C2, denoted by C1 and C2. So if we're going to join that, so this is your optical center, over here is your optical center. Okay, so the centers of the spheres where we took our thin converging lens is the center of curvature. Now related to that is the radius of curvature. So the same thing, we have two spheres and they have both centers here and here, and this is the optical center of your lens. Okay, this is O and this is your C1 and C2. Okay, so distance between C1 and O is the radius of curvature, which is denoted by R, big letter R, R1, and of course this is also R2, and they are equidistant to each other, so that's the radius of curvature, the distance between the center of curvature to the optical center of the lens. Finally, we have the principal axis, as I've been mentioning earlier. So we have all the points over here. So we have the important points. We have, let's have the center of curvature 1. We have the optical center. We have the center of curvature 2. And we have also F1 over here. F1, and we have F2 over here. So if we are going to draw a line joining all of these points passing through the optical center of the lens, this is called your principal axis. Okay, that's the principal axis. It's the imaginary line joining all the important points on your lens. Now, one thing you have to remember though, if we have our lens over here, okay, and we will draw our principal axis. This is our center of optical center. We will draw this line, imaginary line, and we have our focus one over here and F2 over here. Now the center of curvature is somewhere over here. C1. Okay, let me just. This is C1 and this is C2. Now, if O, optical center to F1, let's say is 5. Okay, so O to 5, F2 is also 5 centimeters. Let's say 5 centimeters, 5 centimeters. Okay, now F2 to the center of curvature 2 is also 5 centimeters. Okay, and F1 to C1 is also 5 centimeters. They are all equidistant from each other, like this. This is important because if you're going to draw your ray diagrams, it will be important for you to divide your line, your principal axis, with equidistant according to the specification given to you in the problems. They should all be equidistant from each other. So optical center to F1 and optical center to F2, they are equal to each other. Optical center to C1 and optical center to C2, they are also equal to each other. Now if you are going to divide, they are all equal to each other. Now there are 3 standard rays that we're going to use as rule in drawing ray diagrams. First, we have the standard ray number 1. Standard ray number 1 is very easy. It is a line drawn through the optical center of our lens, and it will go undeviated like this, unbent. Now we have standard ray number 2. Standard ray number 2, let's draw this one. Okay, this is the imaginary line going through the optical center of our lens. Now, the standard ray number 2 is a parallel ray of light, okay, which will hit the imaginary line passing through our optical center, and after hitting this line, it will go through the principal focus on the other side. So this is our standard ray number 2. Now, standard ray number 3 is this way. It's a light ray. Okay, let's draw that. Do it again. Okay. Okay, so this is our imaginary line passing through our optical center. We have a light ray passing through the focus one, and it will hit the imaginary line passing through the optical center. After hitting this line, it will go parallel to the principal axis. So that is our standard ray number 3. Before we go on using these 3 standard rays in drawing our images, we have to define some words first. So first we have virtual image and real image. So what is a virtual image and what is a real image? What's the difference? A virtual image is an image that is formed by imaginary lines. So example, if we have our object here, okay, our object is on the left side and we are going to form an image on its side. Okay, let's say here on the side of the object. So this is a virtual image. It is an image formed by imaginary rays of light. Okay, so it is always found in the object side. How about a real image? Okay, so let's clear that up. If example, our object is over here and we are going to form the image that we formed is on the other side of the lens, then this is a real image. Okay, so it's always on the other side of the lens where your object is. This is your object and this is your image. An image which is formed on the other side of the lens is always a real image. So that's the difference between virtual image and real image. The real image is formed by actual light rays of light, and it is always caught on a screen, whereas a virtual image you won't catch it on a screen. Okay, so next, what is upright and inverted image? So earlier I drew 2 things. The upright image is, let's say our object is over here, and this is, if our object is over here, here is our virtual side. Okay, and if our object is over here again, yeah, this is our real side. Now if your object is on the other side, then of course it will flip also. Now if we have formed an image over here, let's say this one, so this is a virtual image, it's upright image because it's right side up. Okay, a virtual image is always upright. Now if we are going to form an image over here and it is the wrong side down, okay, the top side down, okay, so this is an inverted image. Okay, so real images are always inverted. So that's it for upright and inverted image. Let's go to the next one. What's magnified and diminished image? So let's say we have an object here. This is our object, okay, and we formed an image here which is smaller than the object. This is our image. Okay, so this image is called diminished. Okay, but if we have an object over here and we have formed an image over here on the other side which is bigger than your object, okay, this is your image, then of course this is what we call a magnified image. Magnified. So sometimes we form this images which are the same size as your object, so it's neither magnified nor diminished. You will just say that it is the same size as the object. So that's it about magnified image and diminished image. Okay, how are we going to use the 3 standard rays in forming images using a lens? Okay, so in here we have an object, as you can see on the left side. First, we are going to use the standard ray number 1. This is the standard ray number 1. Okay, so the standard ray number 1 passes through the center of the lens undeviated like this, and then we're going to use the standard ray number 2. This is the standard ray number 2. It will be parallel through the parallel to the principal axis, and after hitting the imaginary line of our lens, it will go through the principal focus. Now the third one, we have Okay, this is standard ray number 2 parallel to the principal axis and then passes through the F after leaving the lens, the principal focus. Now the third one, the standard ray number 3, is passing through the focus one first, and then it will become parallel to the principal axis. So that's your standard ray number 3. It passes through F1 and then leaves the lens parallel to the principal axis. So now you have an image formed over here. So as you can see, let me show that to you. This is the intersection of the three lines, three light rays. Now that is significant because it's where you will form your image, like this. Okay, where the intersection is where your head of the arrow is. Okay, if it's a person in your object, then that's where his head is. Okay, so in here you have formed real and inverted and smaller than the object image. So you have formed a diminished image, okay, because it's smaller than the object. Now in here only 2 of the standard rays are required to work out where they go. You don't need all the 3 standard rays in forming your ray diagrams. In doing your ray diagrams, only 2 would suffice. You could either use standard ray number 1 and standard ray number 2, or standard ray number 1 and standard ray number 3. It's always very safe to use standard ray number 1 because it can go through the optical center undeviated, and as the object is moved closer towards the lens, the image becomes bigger and further away. And we are going to do some ray diagrams tomorrow. We are going to use all of these standard rays so that you would know and you would experience how to do ray diagrams. It's quite technical, but actually it's enjoyable. So what have we learned today? We have defined the basic terms related to a thin converging lens, and we have explained the rules of drawing ray diagrams. I hope you enjoyed the lesson. We are going to do some ray diagrams tomorrow. So this is Miss Teresa signing off. Have a nice day.